Please welcome SVP of Research, Labs, Technology, and Society, James Manyika, and founder and lead of Google Quantum AI, Hartmut Neven.
You know, one of the most far-reaching and exciting parts of what Google Research does is the work that the Quantum AI team does. And it's great to be here with you, Hartmut. And the Quantum AI team has had quite a month between the Nobel Prizes for our colleague Michel Devoret and our former colleague John Martinez, but also the big results we announced yesterday. So hopefully some of you saw that, but we'll get into that shortly. But I think it's worth, before we get into this, it's worth rewinding a little bit what's happened in the last 6 months. In December, you probably all saw the announcement from our Willow chip. And I think the part of that most people paid attention to was the random circuit sampling benchmark result, which is that the Willow chip could do in under 5 minutes what is the world's fastest supercomputer could do in 10 septillion years. But I think the most significant thing was the below threshold error correction, which the field has always thought about for a long time. So those are two big announcements. But fast forward to where we are. But before we dive in, Hartmut, how would you describe what we're trying to do with the Quantum AI team? What's the mission?
So the mission of Quantum AI hasn't changed since our inception, and it's rather simple. We want to build quantum computers that can tackle otherwise unsolvable problems.
And you making progress?
Yeah. Published a roadmap in 2020, right after our first big result, and to explain how do we want to make good on this mission. And there's a hardware track, where we have different milestones to build better and more performant hardware. And of course, there's a software track where we want to show more and more interesting applications.
Well, let's get to that. I mean, so yesterday, glad to say this was the cover of Nature Journal yesterday. There were two key things in those results. One was the quantum echoes algorithm, which is actually the OTOC algorithm. Can you explain what that is and describe what's unique about that, and why is that a special result?
Yeah, maybe to tie this to what you mentioned, our December announcement. You may have seen when you read articles about Google Quantum AI that one sort of computer science history-making events was that we were able to show, look, there is a computation that we can do in minutes on our quantum processors, but it would take a huge amount of time, 10 septillion years, on the best classical computer. And initially we were criticized, maybe this is not quite correct, you didn't run the best classical algorithms. But after this December result, this criticism has completely subsided. So the remaining criticism remained like, yeah, okay, you cooked up this benchmark problem that is easy to do on quantum computers.
This is RCS, right?
Exactly. Right. We call this benchmark RCS, stands for random circuit sampling. And then the critique became, but this is not solving a useful problem that people on Main Street have. So the significance of the result of this week is that we answer this, which was valid criticism. This was only a benchmark. But this week we published the first algorithm that will have uses in various real-world scenarios.
But I think a key part of the algorithm was the fact that it's the first verifiable algorithm. Say what that actually means.
Yeah, so there's a few ways to think about this algorithm. Maybe one way how I like to think about it is it makes good on Richard Feynman's dream, who had recommended, hey, if you want to make predictions for certain systems, in particular those where quantum effects are important, you should use a quantum processor to do this. So this is the first algorithm, actually the nickname we invented for this quantum echoes. So the quantum echoes algorithm is the first algorithm that can make verifiable predictions about quantum systems. And by verifiable, we mean that you could either use a second quantum computer, equally performant, of course, to just double check, hey, was the prediction correct? Or maybe more importantly, or probably more importantly, because it's a prediction about a real world system, you can go directly to nature, run an experiment, and see, are the experimental outcomes matching the predictions?
Right, and I think there are a couple key characteristics of the algorithm. One is this idea that you needed it to be, to be able to do kind of, in order to do the observables, you needed to be resolvable in a long enough time frame, so you had enough time for the signal-to-noise ratio to actually be meaningful. But you also needed to do this other thing called Hamiltonian learning. Can you describe what that is?
Yeah. So the algorithm quantum echoes is not the easiest algorithm to explain. So maybe I try first sort of the version. I have a 15-year-old, and to my delight, he is interested in physics and philosophy, and our favorite place to discuss these things are when we sit in the whirlpool. And typically we sit in the whirlpool at night, and then I don't bother heating up the main pool, so there's this perfectly flat surface of the main pool. So it's excellent to explain quantum mechanics because you can make these very nice wave patterns. You can tap on the surface of the pool, and then these concentric circles go out. And then I can explain our current work. See, if you tap on it and you have a little sensor, let's say in one corner of the pool, and the sensor is observing the waves as they come in and looks how high are the waves, amplitudes, how far away are they, sort of the wavelengths. Then by looking at this, you can learn what's in the pool. Because for water, there will be a certain type of wave, but if you would put oil into it or honey, the waves that arrive are different, and hence it's obvious that this wave pattern teaches you something about the material in the pool.
But you want the waves to last long enough to be able to observe them and then learn something about them, right? That's the...
Exactly. So this is why it's called quantum echoes, because you can see if you want to, you collect, of course, more information about the material, the bigger your pool is, the more the material has the ability to leave an imprint on the wave pattern. But if the pool gets too large, you can imagine the wave gets smaller and smaller in amplitude, and eventually you won't measure anything anymore on the other side. So what we really do in the algorithm is then to reflect it back, create an echo, so that the wave pattern then refocuses close to from where it started. And now you have essentially the best of both worlds. You have a good signal, but one that has collected a lot of information about the underlying system.
And which is what brings us to Hamiltonian learning. Because we often think about machine learning, but what's Hamiltonian learning, and what does that have to do with what you're trying to learn?
So Hamiltonian learning is maybe, for the journalists in the room, this is maybe a key term to remember. Hamiltonian is physics jargon. If you give the Hamiltonian of a system to a physicist, then the physicist feels, oh, I know everything about the system. Because the Hamiltonian, if you have it, allows you to calculate the evolution of the system and make predictions about the system. So here in the Hamiltonian learning that we specifically did with the quantum echoes algorithm is to learn the Hamiltonian that describes the structure of molecules.
Which brings us to the second announcement yesterday, which was, in addition to obviously developing the OTOC, the quantum echoes algorithm, we also did a proof of concept experiment with the University of Berkeley. Can you describe what that experiment was and why that was significant?
Yes, so what James is referring to, we actually published 2 papers. The first was the quantum echoes algorithm. By the way, the technical term is out-of-time order correlator. Sounds maybe fun.
Right.
The quantum echoes may be simpler, but it's this basic idea, that you refocus the signal. So we formulated this algorithm, ran it, implemented on our machines, showed that it's verifiable, showed by very extensive red teaming work that classical machines cannot do it. So we essentially packaged up this algorithm. This is an algorithm ready to go for Hamiltonian learning That's the cover of nature.
Right.
But then, of course, we were also curious, can we apply this to first real-world scenarios? So that's where we teamed up with external collaborators, in particular University of Berkeley. And with those collaborators, we applied this algorithm to learn the structure of some molecules. One had 28 nuclei.
So this is DMBP, which is a type of benzene, right? Which has 15 spins and, what, 28 atoms, roughly?
Yeah, so we essentially used nuclear magnetic resonance machines or data from nuclear magnetic resonance machines to do the Hamiltonian learning with the help of the quantum echoes algorithm.
Right.
And yes, there were two molecules, and the larger one you're referring to was a diphenyl, so it has these phenyl rings. And chemists were interested to know how are they rotated relative to each other. And we used the quantum echoes algorithm to learn how this molecule looks.
So in addition to proving out that this was actually useful, I think you actually also discovered the actual angle, the dihedral angle for this molecule.
Yeah, so the dihedral angle wasn't fully known yet. There's an interesting nuance here that we should emphasize. While the algorithm itself on suitable proof of concept problems, as discussed in the Nature paper, is 13,000 times faster than what you could do on a top supercomputer. These molecules, or these proof of concepts applied to real-world NMR, they are still small enough that in principle, armed with the quantum echoes algorithm and armed with suitable powerful classical machines, you could still have done this calculation. Nevertheless, there were certain questions answered that chemists didn't have the answer to yet.
That's pretty cool. But let's maybe zoom out a little bit. So this is obviously one proof of concept. Can you talk a little bit about the other kinds of applications and other kind of uses that an algorithm like OTOC enables us to look at? What else can we be expecting to get applications about?
Yeah, so this is the first example of a family of applications that we call Richard Feynman's killer app. As I already explained, Feynman had the insight that, hey, classical computers, no matter how big or powerful they become, they will always be woefully inadequate to describe systems where quantum mechanics is important.
Right.
And this area we call quantum simulation. And one example, just discussed, Hamiltonian learning of the structure of molecules. But it has many other applications. It's a more widespread problem than you may think. Let's just pick something very key, energy or energy economy. Let's start with energy production.
Right.
Let's say you wanted to build sort of the silver bullet of power plants, a nuclear fusion reactor, which we don't have today. If you wanted to simulate the processes going on in plasma, a quantum computer would be a beautiful tool.
Right.
Or you want to transport now this energy, wouldn't it be nice if we had high temperature superconductors that could transport the electrical power lossless? And finally, you want to store it. Let's say in your car, make lighter, faster charging batteries. Maybe that light and that safe that we can have in electric airplanes, not just electric cars.
Right. Yeah, and in fact, I think, correct me if I'm wrong, I think the community, the people working in the quantum field, have identified something like over 70 algorithms where there seems to be kind of these applications and algorithms that have where there's a quantum advantage. Is that roughly right, 70 or more?
Yeah, there is a site, a website called the Quantum Algorithm Zoo, and it keeps track of all the algorithms that are known which have an advantage where quantum computers have an advantage. And quantum simulation, this whole area, this family of algorithms, is essentially one out of those 70.
Right. Maybe we can shift a little bit and maybe let the audience into a conversation you and I have always had a running discussion about, including actually with Demis, but we always have a fun debate with this, which is, to what extent is quantum helping what we're doing in AI, and vice versa? To what extent is AI actually helping advance the work we're doing in quantum? Can you talk a little bit about that?
Yeah, so we are called Quantum AI for a reason. I did AI before doing this, a lot of object recognition, computer vision, and over time appreciated the fact that AI, as we do it today on classical computers, will not be able to handle certain tasks we really care for solving. But quantum AI, that is AI with access to a quantum computer or access to quantum resources, as we call it, would be able to do tasks out of range for
what's an example of that?
So let's maybe start again with this week's announcement. We had these marvelous successes in protein folding to learn, another Nobel Prize for Google, two Nobel Prizes. So to learn the 3D structure of proteins. Now, a fact that's a little bit less appreciated is that the databases, or I should say it like this, AI needs training data to learn from. And for example, for this protein folding problem, the databases took 50 years to make. So the protein database started in 1970. So there was a lot of sweat from PhD students over many decades to produce this data. And I mentioned fusion earlier. We calculated that just having 1 second worth of data stream, experimental data stream, bringing plasma into conditions conducive to fusion reactions with current technology costs $1 trillion to make. So one beautiful application of quantum computing towards AI is to produce high valuable data sets that AI can use to train.
And in the other direction, how is AI helping make progress in quantum?
Since AI started about 25 years earlier than quantum computing, let's say if you put the start date and the Alan Turing paper, the imitation game that was 1950, and then Richard Feynman's famous speech was in, I think, 75 when he introduced quantum computing. So they have a head start of 25. But because they have a head start, we use plenty of methods from our colleagues from Google Research or DeepMind to help our roadmap, the hardware and the software track. So for example, we use plenty of AI methods to help with the chip design or processor design. Actually, for the NMR paper, we used Alpha Evolve, exactly, to optimize the circuits we used for the quantum echoes algorithm. Or last year we had a nice paper together with DeepMind, was called Alpha Qubit, where we used transformer neural networks to help with an important problem in quantum error correction, the so-called decoding problem.
Right. Well, so stepping back, I mean, so there's a lot more still to do. We have a long way to get to a large-scale, fully error-corrected quantum computer. What are some of the things you're looking forward to in the next year or two? What can we look forward to in the next year or two?
Yeah, I mentioned our roadmap. So the next milestone we expect is on our hardware roadmap, where we broke down getting to a useful quantum computer, which we somewhat arbitrarily defined as a quantum computer with 1 million physical qubits, which we orchestrate to 1,000 very well-protected logical qubits. So with such a machine, we feel you can confidently do important problems and generate economic value. And it's 6 milestones that get us there. The 2 first ones we already cleared, and now we are sort of close to the midpoint, which is milestone 3. And that will be a single, very well-protected logical qubit that can participate in about 1 million algorithmic steps. So we can run more interesting, more complex algorithms.
Well, thank you, Hartmut. I think we'll look forward to see what happens at the next milestone. But thank you. Join me in thanking Hartmut for the incredible work that the team's doing.
Yeah.